The research paper investigates Gevrey regularity of formal power series solutions for a class of nonlinear moment partial differential equations. It generalizes results from linear partial differential equations and linear moment differential equations. The study focuses on equations of the form 1, where the inhomogeneity is sigma Gevrey with respect to the time variable t for a fixed sigma E0. The authors analyze the geometric structure of the Newton polygon associated with the equation to achieve their results. They show that the Gevrey regularity of the formal solution depends on the Gevrey regularity of the inhomogeneity and the structure of the equation. The paper is structured into sections, starting with definitions and properties of moment functions and Gevrey formal power series. It then introduces the notion of modified Nagumo norms and the main problem considered, which is the study of the Newton polygon and the uniqueness of the formal power series solution. The main result connects the critical value of the equation with the Gevrey order of its formal solution. The paper concludes with a detailed example and the proof of the main theorem. Here is a combined summary of pages 3 and 4 of the research paper. In the context of Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, we define a sector of an infinite radius, denoted by SDP alpha, as an open set in the complex plane. We also introduce the notation OPUC to represent the set of all holomorphic functions defined in an open set U. We then delve into the concept of moment functions and moment differential operators. A pair of C-valued functions, P, EQ, is called a kernel function of order S if it satisfies certain conditions, including holomorphy on a specific sector, exponential decay at infinity, and integrability at 0. The function E is connected to the kernel function E through a moment function M, defined by the Mellin transform of E. We also define a moment sequence of order S as Pmkia 0, where M is a moment function of order S. To generalize the definition of kernel functions to all positive orders S is greater than or equal to 2, we introduce an adjusted definition of kernel functions, which involves a kernel function of order Sp, where p is a positive integer such that Sp is less than or equal to 2. The paper provides an example of kernel functions and their corresponding moment function, which is widely used in the classical theory of K-summability. We also state a proposition regarding the holomorphy and asymptotic behavior of moment functions, which implies the existence of positive constants c, a, and a such that the estimate, mpjq, is less than or equal to Caj gamma. 1 plus Sj, jq holds for all j is greater than or equal to 0. Furthermore, we introduce the concept of regular moment functions, which are moment functions that satisfy certain estimates involving the gamma function. An example of a regular moment function is provided, and its regularity is verified using Stirling's formula. The research discusses Gevrey regularity for inhomogeneous nonlinear moment PDEs, focusing on moment differentiation and its properties. It introduces the notion of moment differential operators or moment derivatives, which were first proposed by W. Balcer and M. Yoshino. The concept of moment derivation is defined, extending naturally to analytic functions at the origin of C(n). The paper proves that if a function is analytic on a polydisk and its moments are regular, then the moment-derived function also defines an analytic function on the same polydisk. This result is demonstrated through a proposition and its proof, which involves estimates and convergence properties of the moment-derived series. The research provides a significant contribution to the field by clarifying the properties of moment-derived functions and their relation to analytic functions, particularly in the context of inhomogeneous nonlinear moment PDEs. In the context of moment differential equations, this paper discusses the concept of Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs. It introduces the notion of Gevrey order, which is a measure of the growth rate of coefficients in a formal power series. The paper also explores the algebraic structure of the set OPD ρ1, ρnqrrts is sigma, showing that it forms a C-differential algebra under certain conditions. The authors then delve into the concept of modified Nagumo norms, an extension of classical Nagumo norms tailored to moment differential operators. These norms are defined based on the idea of majorant series and provide a way to measure the size of an analytic function on a polydisk. The modified Nagumo norm, f, alpha, r, s depends on the indices, alpha, r, s, and is used to quantify the growth rate of the coefficients of a formal power series. This norm is essential for studying the convergence of formal solutions to moment PDEs and can be applied to establish the existence of actual solutions. The paper further discusses the stability of the set OPD ρ1, ρnqrrts's sigma under moment derivatives when considering regular moment functions. This stability is crucial for the study of inhomogeneous nonlinear moment PDEs and their formal solutions. By introducing the concept of modified Nagumo norms, the authors aim to create a tool that can be used in the framework of moment differential operators, similar to standard Nagumo norms in other contexts. The paper concludes by emphasizing the importance of these new concepts in the study of moment PDEs, highlighting potential applications in various fields such as mathematical physics and engineering. The proposed framework provides a systematic approach to analyze and solve inhomogeneous nonlinear moment PDEs, contributing to the advancement of research in this area. In the context of Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, this section discusses the properties and applications of modified Nagumo norms. These norms are defined as a generalization of classical Nagumo norms, with the introduction of a new parameter alpha. The modified Nagumo norms have been shown to be well defined and to possess properties similar to the classical Nagumo norms, such as the triangle inequality for the product of two functions. This is demonstrated through several lemmas and propositions, including the adaptation of a result from 24 for the product of two functions. The first proposition, 4.4, demonstrates that the modified Nagumo norms are indeed norms on the space OPD ρ1, ρnq. This is achieved by showing that the function f, alpha, r, s defines a norm, i.e., it satisfies the non-negativity, absolute homogeneity, and triangle inequality properties. The next two lemmas, 4.5 and 4.6, provide technical results that will be used in subsequent proofs. Specifically, they deal with the behavior of the coefficients in the majorant series and their relationship to the parameters alpha and beta. These results are essential for establishing the properties of the modified Nagumo norms. The final proposition, 4.7, is an adaptation of a result from 24, which demonstrates the triangle inequality for the product of two functions in OPD ρ1, ρnq. This result is crucial for establishing the properties of the modified Nagumo norms and their applicability in the context of Gevrey regularity for inhomogeneous nonlinear moment partial differential equations. In the context of inhomogeneous nonlinear moment partial differential equations, this research delves into the properties of modified Nagumo norms and their relationship with Gevrey regularity. The first result, proposition 4.7, establishes that for all alpha, beta in the interval 1, infinity, and s in r⁻n, the modified Nagumo norms satisfy the inequality fg alpha beta r s is less than or equal to r lambda beta f alpha r s g beta r s. This proposition is essential for understanding how these norms interact with each other under different parameters. Following this, corollary 4.9 is derived, which states that if m1, mn are regular moment functions, then for all alpha in 1, infinity, and q in n⁻n, there exists a positive constant c such that b⁻q_m x alpha q r s is less than or equal to c lambda q n airy product d equals 1 n sd alpha d q d1 f alpha r s. This corollary demonstrates the connection between the modified Nagumo norms and the concept of Gevrey order of a formal power series. Proposition 4.12 explores the relationship between Gevrey regularity and the modified Nagumo norms. It asserts that if U, X, T, is a sigma Gevrey formal power series, then for all alpha in 1, infinity, S in r⁻n, and J in n, there exist positive constants A, B such that U_J, X, alpha, R, S is less than or equal to AB⁻J gamma, 1 plus sigma J. This result bridges the gap between the theory of Gevrey regularity and the practical application of modified Nagumo norms. Lastly, Proposition 4.13 addresses the issue of bounding the pointwise values of a function using its modified Nagumo norms. It claims that there exists a positive constant a such that for all f, x, in op. d underscore rho, and alpha in 1. Infinity, the inequality, f, x, is less than or equal to a lambda, alpha, f, alpha, r, s holds for all x in d underscore rho. This proposition provides a practical means of estimating the pointwise values of a function using its modified Nagumo norms. In conclusion, these results collectively contribute to a deeper understanding of the interplay between modified Nagumo norms, Gevrey regularity, and the properties of inhomogeneous nonlinear moment partial differential equations. They provide a framework for researchers to analyze and solve such equations, leveraging the tools of Gevrey theory and the practicality of modified Nagumo norms. The paper discusses the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs, of the form given in equation 8. It focuses on the formal well-posedness of these equations, which is proven in proposition 5.1. The proof involves expressing the coefficients of the formal solution in a recursion formula, 10, and initial conditions. This requires the use of moment multinomial coefficients and a specific notation for the sum of terms in the recursion formula. The paper also provides a detailed explanation of the notation and the conditions under which the third sum in the recursion formula is 0. Additionally, it clarifies that the term in equation 11 is 0 when a specific condition is met. The overall goal is to establish the formal well-posedness of the inhomogeneous nonlinear moment PDEs, which is crucial for understanding their behavior and potential applications in various fields of mathematics and physics. The paper discusses the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs, focusing on the moment-Newton polygon associated with these equations. It begins by defining the moment-Newton polygon as the convex hull of a set of points, each representing a term in the PDE. The geometric structure of this polygon is determined by the sets S and S_n, which are defined based on the moment functions and their properties. The authors present two main cases for the moment-Newton polygon's geometry: when S is empty, case 1, and when S is non-empty, case 2. In case 1, the polygon is reduced to the domain C, PS0 kappa, meaning it has no side with a positive slope. In contrast, in case 2, the polygon has at least one side with a positive slope, and its smallest positive slope k is given by a specific formula. This slope is determined by the tuple pi q r from S_n that minimizes the expression. The paper also provides a proof for these two cases, using the properties of the sets S and S_n. It highlights that the condition S equals empty set implies that all points representing terms in the PDE lie within the domain C, PS0 kappa, resulting in a polygon without any positive slope. Conversely, when S is non-empty, the polygon must have at least one positive slope, and the smallest such slope is calculated using the minimizing tuple pi q r from S_n. The paper concludes with a detailed explanation of the moment-Newton polygon's geometry, emphasizing its importance in understanding the Gevrey regularity of solutions to inhomogeneous nonlinear moment PDEs. The geometric structure of the polygon is crucial for determining the properties of these solutions, particularly their regularity and behavior near singularities. Here is a combined summary of pages 17 and 18 of the research paper. The paper introduces the concept of critical value sigma c for inhomogeneous nonlinear moment partial differential equations, PDEs. Specifically, sigma c is defined as the non-negative real number satisfying certain inequalities involving the segment with endpoints PS0 kappa cond ni L, 1 PS0 RLIL RL lambda PSQLQQ, V, Q, Rni L, 1 RLIL. This definition is used to derive fundamental inequalities in proposition 5.6, which states that for sigma is greater than or equal to sigma c, certain inequalities hold for all n in N and all pi, q, r element of p lambda n. The proof of proposition 5.6 involves adapting the proof of 22, lemma 3.9, and considering two cases. When S equals H and when S does not equal H in the first case, sigma C equals 0, and the inequalities follow directly from the definition of the set S in the second case. Sigma C is defined as a non-negative real number, and the inequalities are derived using this definition. The main result of the paper, Theorem 5.7, states that if sigma C is the critical value of EQ 8, then 1. Rupt, XQ and RFPT, XQ are simultaneously sigma Gevrey for any sigma is greater than or equal to sigma C, and 2. Rupt, XQ is generically sigma C Gevrey while RFPT, XQ is sigma Gevrey with sigma less than sigma C. Before proving Theorem 5.7, a corollary 5.8, is formulated, which deals with convergent inhomogeneity RFPT, XQ. This corollary states that if the inhomogeneity is convergent, then the formal solution Rupt, XQ is either convergent or 1, K Gevrey, where K is the smallest positive slope of its associated moment Newton polygon. An example 5.9, is also provided, illustrating the semilinear regular moment heat equation. The research discusses the Gevrey regularity for inhomogeneous nonlinear moment PDEs, focusing on the moment Newton polygon and its implications for the critical value and solution regularity. It begins by analyzing the moment Newton polygon associated with equation 12, highlighting the critical values definition and its relation to Gevrey regularity. The discussion then shifts to the generalized regular moment Suwińska equation 13, and its associated moment Newton polygon, demonstrating a similar approach. Lastly, the paper examines the generalized regular moment Burgers-Korteweg-Vries equation 14, emphasizing the importance of the smallest valuations in the polynomial coefficients for the moment Newton polygon. Throughout, the research emphasizes the connection between the moment Newton polygon, critical values, and Gevrey regularity, providing a comprehensive analysis of these concepts in various nonlinear moment PDEs. The paper discusses the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations (PDEs). It begins by explaining that the critical value of a specific equation is given as sigma C, $0 if Q1's 1 is 0, and Q1's 1 is 0 otherwise. The authors then proceed to prove the first point of Theorem 5.7, which involves the use of modified Nagumo norms, majorant series, and a fixed point procedure. They introduce the concept of multi-index alpha, which is determined by the maximum of V, Q, R and the minimum of sigma S0, with sigma S0 being a positive number. The authors also define the Gevrey regularity for the unique formal solution Rupt, XQ of the inhomogeneous nonlinear moment PDEs. The paper continues with the second step of the proof, where they derive recurrence relations for the coefficients uj, pec of the formal solution. These relations are based on the equations 10 and 11 from the paper, and they involve the use of a multi-index alpha and the modified Nagumo norms. The authors also present the expression for Pj kappa q alpha s in terms of a sum over L and a product of H and Ph ILQ. This expression is crucial for establishing the Gevrey regularity of the formal solution. The paper concludes by summarizing the key points of the proof, including the use of the modified Nagumo norms, the majorant series, and the fixed point procedure. It also highlights the importance of the multi-index alpha and its role in determining the Gevrey regularity of the unique formal solution. The paper demonstrates that the Gevrey regularity of the formal solution of the regular moment Korteweg-Vries equation and the regular moment Burgers equation can be established using this methodology. The research paper discusses Gevrey regularity for inhomogeneous nonlinear moment PDEs. It begins by observing that assumption 5.3 implies certain inequalities for the components of alpha 1 sigma, which in turn satisfy the conditions for proposition 4.7 and corollary 4.11. This leads to the definition of B1I, Q, R, J, N and its bound, which is crucial for the subsequent analysis. The second step involves bounding B1I, Q, R, J, N, utilizing the definition of M0 and the properties of kappa. The paper then proceeds to establish inequalities for M0 pH ILQ and its relationship with IL. These findings are used to derive inequalities for n's and its relationship with RL. The Stirling's formula and assumption 5.3 are applied to further constrain these values. The overall goal is to demonstrate the Gevrey regularity for the inhomogeneous nonlinear moment PDEs, showcasing the intricate relationships between various components and their bounds. In the context of inhomogeneous nonlinear moment partial differential equations, PDEs, this paper discusses the Gevrey regularity for solutions to these equations. The authors introduce a modified Nagumo norm, denoted as Uj, which is used to establish the regularity of solutions. The paper also employs the classical majorant series method to bound this norm. The authors start by defining a constant C4, which is a positive constant that depends on the number of variables n. They then use this constant in conjunction with other previously defined constants and functions to derive an inequality, 18, that provides an upper bound for the modified Nagumo norm in terms of various parameters, including the constant C4, the function I, Q, R, J, the function sigma pj0q, R, S, and the gamma function gamma p1 sigma j0q m0 pj0q. This inequality is crucial for establishing the Gevrey regularity of solutions to the inhomogeneous nonlinear moment PDEs. Following this, the authors proceed to derive another inequality, 20, that involves the modified Nagumo norm and several other functions and constants. This inequality further refines the upper bound established in 18, and provides a more precise estimate for the modified Nagumo norm. The paper then transitions to the third step of the analysis, where the authors utilize the classical majorant series method to bound the modified Nagumo norms, Uj, j for any j is greater than or equal to 0. To do this, they defined two new functions, gj, s and alpha I, q, r, j, s, and use these functions to prove a technical lemma. This lemma is essential for completing the proof of the Gevrey regularity for solutions to inhomogeneous nonlinear moment PDEs. Overall, this portion of the paper presents a detailed analysis of the Gevrey regularity for solutions to inhomogeneous nonlinear moment PDEs. The authors employ a combination of mathematical techniques, including the use of modified Nagumo norms and the classical majorant series method, to establish upper bounds for these norms and ultimately prove the desired regularity result. The combined summary of pages 27 and 28 of the research paper discusses the Gevrey regularity for inhomogeneous nonlinear moment PDEs. It begins with lemma 6.1, which establishes inequalities for the functions gj, s and alpha I, q, r, j, s. The proof relies on corollary 4.9 and proposition 4.12. The discussion then shifts to the formal power series Vpxq, where the coefficients are recursively determined by relations involving gj, s and alpha I, q, r, j, s. The initial conditions for the Vj's are also specified. Proposition 6.2 proves inequalities for the Uj's, assuming the inequalities hold for all k less than j for a certain j. The proof involves applying the hypotheses to relations and using the initial conditions. The summary concludes by highlighting the novel ideas and significant findings presented in these pages, including the Gevrey regularity and the inequalities for the Uj's. Here is the combined summary. The relations presented in Proposition 6.2 are utilized to establish the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations. Specifically, the formal series Vpxq is proven to be convergent, and two positive constants C1, K1 greater than 0 are identified such that Vj is less than or equal to C1 K1j for all j is greater than or equal to 0. To demonstrate the convergence of Vpxq, the functional equation, 25, is employed, where alpha pec and hpxq are formal power series defined by specific expressions. The coefficients of these power series are non-negative, and they define increasing functions within their respective regions of convergence. By applying the fixed point method, a formal power series Vpxq is defined, which is a solution to the functional equation, 25. It is shown that Vpxq converges to Vpxq by uniqueness. Furthermore, the v-micro-Peck functions are analytic on a disk with centers 0 in radius min, tr alpha, rh, and they are of order x micro. The convergence of Vpxq is established by bounding the coefficients rc micro, rr, which are generalized Catalan numbers. This leads to the normal convergence of Vpxq on any disk with centers 0 in radius less than a specific value. Consequently, Vpxq is analytic at 0, completing the proof of proposition 6.3. The implications of propositions 6.2 and 6.3 are then used to bound the modified Nagumo norms, uj, j as, r, s. Specifically, corollary 6.4 states that, uj, j as, r, s is less than or equal to C1 K1 JM0 PJQ gamma P1 sigma JQ for all j is greater than or equal to 0. Finally, this result enables the completion of the proof of the first point of theorem 5.7. The paper discusses the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations (PDEs). It begins by introducing an auxiliary function EMPXQ, which is defined as a sum of terms involving the regular moment functions MDPJQ. This function is shown to be analytic on the polydisk D1, 1. The authors then proceed to prove the first point of theorem 5.7, which involves demonstrating that the formal solution rupt xq of the inhomogeneous nonlinear moment PDE is sigma Gevrey. They use a series of inequalities and calculations to establish this result, leveraging the properties of the Gevrey spaces OPD rho 1, rho NQRRTSSs and the definition of the function EMPXQ. Next, the authors focus on the second point of theorem 5.7, where they assume that S per mil handfix 0 d sigma is sigma c. They introduce a new equation, 26, with specific conditions on the coefficients I, Q, R, the initial conditions phi jpxq, and the inhomogeneity RFPT, xq. They also provide a simpler form of this equation in remark 6.7. Finally, the authors prove that the formal solution rupt xq of the new equation, 26, is exactly sigma c Gevrey. To do so, they rewrite the general relations, 10, as identities involving the terms uj kappa, Peck and rjpxq. The proof then involves showing that rupt xq is not sigma 1 Gevrey for any sigma 1 a sigma c, using the properties of the Gevrey spaces and the definition of the function EMPXQ. Here is the combined summary of pages 33 and 34. The paper discusses the Gevrey regularity of inhomogeneous nonlinear moment partial differential equations (PDEs). The authors consider a system of PDEs with coefficients I, Q, R, initial conditions phi j, and inhomogeneity RFPT, xq. They assume certain hypotheses on the coefficients, initial conditions, and inhomogeneity. Using these hypotheses, the authors derive an equation for Uchpli, Q, R, which involves the coefficients I, Q, R, initial conditions phi j, and inhomogeneity RFPT, xq. They then apply lemma 6.5 to bound the term become, x phi inpec, which is expressed in terms of the moment function m0. The authors also use the regularity of the moment function m0 to bound the term m0 pkv, q, r kappa, inc v, q, rq. This bound is crucial in establishing the Gevrey regularity of the solution uj. The authors then apply lemma 6.8 to bound the term j, 1 zik, 0 v, q, Urzel, 1, v, q, r kappa, inc elf, 0. This bound is used to establish the main result, proposition 6.6, which states that the solution uj is not sigma 1 Gevrey for any sigma 1 a sigma c. The proof of proposition 6.6 involves a contradiction argument. The authors assume that the solution uj is sigma 1 Gevrey and derive a bound on the term Uchpli, q, r kappa, inc in, p0q. They then use the properties of moment functions and the definition of sigma c to show that this bound is impossible, thus establishing the result. The paper also includes a proof of lemma 6.8, which is a technical result used in the main proof. The lemma states that for any integer a0, J, 1 Zeke, 0 Wiesel, 1 PKPV AQ LICFJVQ. The proof involves an induction argument on J. In the context of moment partial differential equations, the paper explores the Gevrey regularity of formal solutions to inhomogeneous nonlinear equations. The authors delve into the relationship between the Cauchy-Kovalevskaya theorem and the results obtained from their research, highlighting potential areas for further study. They also provide a comprehensive list of references that underpin their work, encompassing various aspects of differential equations, Gevrey classes, and summability. The paper begins by discussing the case where the moment functions are chosen such that m0, lambda, equals m1, lambda, equals mn, lambda, equals gamma, 1 plus lambda, reducing the moment PDE to a classical inhomogeneous nonlinear partial differential equation. This allows for the examination of the Gevrey regularity of its formal power series solution, including the non-Kovalevskaya case, using the main theorem of the paper, Theorem 5.7. The authors then contrast their findings with the Cauchy-Kovalevskaya theorem, which states that the formal solution of a Kovalevskaya-type PDE defines an analytic function at the origin of C2. In comparison, the paper's result is weaker, as it only provides one Gevrey regularity. This discrepancy suggests an opportunity for future research to strengthen the result, perhaps through a different choice of Newton polygon or calculation method. The paper concludes with a detailed list of references, showcasing the breadth of research in the field of differential equations, Gevrey classes, and summability. These include works by notable authors such as Balcer, Nagumo, Palya, Shigo, and Yanamura, among others. The list also includes recent studies by the authors themselves, emphasizing their ongoing contributions to the field. In summary, the paper presents a comprehensive analysis of the Gevrey regularity of formal solutions to inhomogeneous nonlinear moment PDEs, drawing connections to the Cauchy-Kovalevskaya theorem and highlighting avenues for future research. The extensive reference list underscores the depth and breadth of the research, providing a valuable resource for scholars in the field.